Hello, good morning to everyone. Today we are going to discuss about the capacitive transducers. Capacitive transducers are another type of transducer as like inductive transducer. In this case, the basic principle of capacitance that is used to transform a physical form of energy into electrical signal. Now, these type of transformers are used for linear or angular displacement. So let us look at the structure of a capacitive transducer. So this is the basic structure of a capacitive transducer, where you will find two metallic plates. This is indicated by this red colored upper metallic plate and lower metallic plate. In between, you will find a material which is called the dielectric material, which is like an insulating material. So this is the basic structure of a capacitance. So there's an upper plate, a lower plate. The thickness of this plate is notated, indicated by X. The width of the plate is like W. Then L is the length of the plate, and of course this dielectric material has got some dielectric constant, which is epsilon R. This is we are going to discuss soon. Now the basic principle behind the capacitance capacitor. The capacitance of a parallel plate capacitor is given by C, which is the capacitance, is equal to epsilon A divided by X, where epsilon is called the permittivity, and this permittivity has got two parts. One part is epsilon 0 and the other part is epsilon R. Epsilon R is a constant and is called the absolute permittivity, and its value is 8.854 into 10 raised to minus 12 farad per meter. Epsilon R is the relative permittivity, which is again the permittivity of a medium with reference to air or some other reference. So for example, if you are looking at epsilon R of air, which is equal to 1, because normally we are considering the permittivity of a medium with respect to air. Now A is the area of the plate, which is in meter square, and D is the distance between the plates in meters. So as per this particular definition, we can see that the C is directly proportional to A, which is the plate, and it is inversely proportional to the distance between them. So there are two possibilities available. If you want to change the capacitance, one way is you can change the area, the overlapping area or the area between two plates. So we can make one plate is movable and other plate is fixed, and the overlapping area is an indicator or is a measurement of or is a function of the capacitance. And another point is that if you can change the distance of the plate, increase or decrease the plate. So this is also another example. Now this dielectric material could be even air. Air can be considered as a dielectric material. So suppose if you expect a vertical motion, there is a vibration or displacement is going to happen in the vertical, up and down direction. That will cause an increase or decrease in X or change in X, and this change in X is going to make some change in the capacitance value. So the same expression can be expanded as C is equal to epsilon 0 epsilon R A divided by X. So in the case of air dielectric capacitors, or if the dielectric is air, then the epsilon R is going to be 1. Epsilon 0 is the relation already we have given, the constant value, which is 8.854 into 10 raised to minus 12 farad per meter. Now another important point is, what is the sensitivity of the parallel plate capacitor? Normally that is calculated by differentiating DC with respect to X. So epsilon into A is a constant term, then we have to differentiate 1 by X, we will get minus 1 by X square. So if you substitute, we will get DC by dx is equal to epsilon A divided by X square. This part is normally called as the sensitivity of the capacitance, how fast or how sensitive the capacitor is. So that is calculated by the equation epsilon A divided by X square. So from this it is very clear that this the value of X is having more influence on the sensitivity than the area of the plate. So let us look at two different practically used capacitive transducer. Number one is the cylindrical capacitive transducer. In this particular model, there are two tubes out there. Okay? One is the fixed metal tube, and another one is a movable metal tube. And this movable metal tube is attached to the system whose displacement is to be measured. And there is a space in between these two cylinders. So let us assume that the diameter, the inner diameter of the fixed metal box is D1, and the moving metallic tube is D2, and there is a space is there in between. And this space is something but the space that is required for the dielectric material. So most probably they are using in system using air is the dielectric. So what is going to happen as the part is displaces, which will cause this particular moving tube to occupy the space in the inner cylinder, and definitely it will give rise to a situation of an overlapping space. So there is a space is there, and up to then depending upon the nature of the displacement and depending upon the quantity of the displacement, some part is occupied, some part of this moving tube is occupied inside the fixed metal tube. So the mathematical relations for calculating a cylindrical capacitance is C equal 2 pi epsilon x divided by the natural logarithm, which is ln of d2 divided by d1, where x already we defined it is the overlapping distance. Now d2 is nothing but the diameter of the smaller tube, whereas d1 is nothing but the diameter of the bigger tube. So ln of d2 divided by d1, that is the denominator part. So just this d2 is nothing but the diameter of the inner tube, whereas d1 is, the fixed metal tube, whereas d1 is the diameter of the moving tube. So d1, d2 are the corresponding diameters of the cylinders. As we said again, d2 is the diameter of the fixed metal tube. It's normally bigger, and the diameter of the moving tube is d1, which is normally smaller, and the space will be occupied by the dielectric. Now again, the main concern is the sensitivity, how sensitive it is here. So we just use the symbol dou c divided by dou x, or the partial of c with respect to x, because c is dependent upon many other parameters. So in this particular example, d2, d1 is going to be fixed. The only thing which is going to change is the overlapping distance. So if you are going to differentiate this particular expression, we'll end up with a relation to 2 pi epsilon divided by ln of d2 divided by d1. This is the sensitivity which is in farad per meter. Another example is like what? Parallel plate capacitance transducer. There are two plates are there. This plate is moving one over the other. Again, the space between these two plates will be occupied by some kind of dielectric. Assume that we have got a plate of width W, and an overlapping part is called X. One part is, one metallic plate is fixed plate, and this plate is movable plate, and this is attached to a part that is whose displacement that is to be measured. The space for the dielectric material, which is indicated by X. Again, from the relation C is equal to epsilon A divided by D. So in this case, what is important is we are interested in the overlapping area. The overlapping area is obtained by W multiplied by the corresponding W and X. W multiplied by X, where W is the width and X is the distance of overlapping. So here in this example, we are using D for the distance of separation. Assume that this is D. So what we will get in this expression, W is the width of the dielectric in meters, X is the overlapping distance, which is again in meters, D is the distance between plates, which is meters. So if you find out the sensitivity dc over dx, we'll get epsilon W divided by D in farad per meter. So what you can understand that in both cases, whether it is like a parallel plate capacitance transducer or cylindrical capacitance transducer. What is most important point is the overlapping distance. The overlapping distance that determines the value of capacitance. So these type of capacitors can be used for measurement of displacement, linear displacement. So now we'll also look at the capacitance transducer that can be used for measurement of angular displacement. So in this particular example, we have a fixed plate, it's like a half circle. We have a half circle fixed plate, and we have another half circle movable plate pivot on a common axis. The center of what you call the fixed plate. So these two plates are aligned in such a way that they are concentric, or they have got a common center in between. So let us assume that the radius of the plate is r, and it is designed in such a way that the movable plate can easily rotate with reference to the fixed plate, and normally it is used for the measurement of angular displacement. So the part which is under movement or having angular displacement supposed to be attached to this particular moving plate or the movable plate, and that will cause some displacement. So again, we look at the relations here. C is equal to epsilon A divided by D. Now in this particular example, we try to calculate the C max, the maximum value of the capacitance that can be obtained from capacitance transducer is calculated by the equation epsilon divided by D. Now the maximum coverage is going to happen is like what? The half circle, because once it is completely rotated, then we'll have the full half circle overlap. So that is obtained by the half of the area of the circle whose radius is r. We'll find half pi r square. So epsilon by d is the same term into half pi r square. So if we just rearrange the equation, we'll get pi sigma r square divided by 2d. So this is the maximum amount of the capacitance value, or the capacitance value without maximum overlap. It can also be calculated based on the angle theta. So let us assume that this is the reference axis. So this angle is theta. So you can change this angle from 0 until a maximum of 180 degrees. So we will get maximum C max, the maximum value of C max when theta is equal to 180 degree. So the same logic if you apply here, we found C is equal to epsilon into theta r square divided by 2d. But be careful here, this theta is angular displacement in radians, so supposed to be in radians. Okay, now the sensitivity can also be calculated by the equation S equal to dou C divided by dou theta, since this is the only parameters which is changing. So we'll get an equation sigma r square divided by 2 times d. So this is the end of this capacitive transducer lecture. We'll have more applications of these type of transducers in the coming lecture. Thank you for watching.